I'd like to invite the final speaker of this session. It is Adeel Ahmed, who is a final year PhD candidate at the University of Hertfordshire. He's a graduate in pharmaceutical science from the same university and currently working in the Department of Clinical, Biological and Pharmaceutical Science, and is working on cell culture models, which you're going to tell us about today.
Thank you for the kind introduction. So today I'm going to talk to you a bit about my PhD project at the University of Hertfordshire, which was conducted in collaboration with CM Bio Innovations. So our airways are very complex, and they have a complex anatomy. Alongside that is the very complex tissue substructures within them. We want to look and model each of those tissues realistically and reliably, to evaluate the crosstalk between the tissues, especially the epithelium and the smooth muscle. If we can create a cell model of these tissues that replicates the realistic tissue architecture and the correct cell signaling, we can evaluate biological processes and responses such as allergenic bronchoconstriction. But why do we need these cell models? Yesterday, we heard a really good talk about the need for more predictable models by Professor Trainee. And we all know that animal models just lack that human relevance to be a predictable, a powerful tool for predictability. So the thing that has been developed and further developed is these human relevant cell culture models. Taking conventional cell culture that extra mile by utilizing microphysiological systems, incorporating things such as perfusion and mechanical stretch, as well as creating a 3D complex structure to replicate what we see in vivo. The microphysiological system that I utilized in my project was the physiomimic system developed by CM Bio Innovations. This system is a totally perfused system using an open well format. The system itself uses a docking station and drivers that sit within the incubator, and then a plate where the cells are cultured on, and a controller that sits outside of the incubator for control over the flow, which is completely tunable. There are multiple plates that can be used with the physiomimic system. The barrier plate was the plate that I utilized throughout my project. And each of these wells were cultured using transwell inserts with the perfusion in the basolateral chamber across each of those wells. So each individual well was an individual organ on a chip. So the first barrier, the first tissue that we tried to replicate was the epithelium. And I used the Calu-3 bronchial cell line, as it's a well-used and well-understood cell line, human cell line. And in air-liquid interface, shows a lot of the features that we see in native human bronchial epithelium. So the first objective was to evaluate the effect of perfusion on our Calu-3 model. So how that was done was growing the Calu-3 cells on this transwell with the perfusion and without the perfusion. So we can see the cells were seeded and then raised to ALI after 48 hours, and then cultured for 14 days in the perfused system. And at day 7 and day 14, permeability of the barrier was evaluated using a sodium fluorescein permeability assay. Throughout the culture, we also assessed the barrier function using tear measurements. So what we saw was the perfused system created a more consistent barrier throughout the 14-day culture, and we can see that in the tear, where the tear in the perfused system is not as variable as it is in the static system. And that translated into our apparent permeability, where at day 7, the perfused system had a lot lower permeability than the static system. In fact, it took the static model almost 14 days to get to the same point. So we established here that the perfused system is decreasing the variability within the plate and between the wells, as well as creating a functional barrier 7 days sooner than the static. So now that we have a epithelial model and we've evaluated the effect of perfusion, the next step is to add that smooth muscle layer in so we can start having that crosstalk. So we seeded the smooth muscle cells on the basolateral side of the same transwell as the Calu-3 and cultured them together for 7 days in ALI conditions, again with the perfusion and without the perfusion. We also evaluated the mucus expression throughout the culture on days 3 and day 7, and again looked at the barrier functionality using the sodium fluorescein permeability assay. We also characterized each of the cells using qPCR. So the first thing that we needed to ensure was we are expressing the correct morphology and phenotypes of our cells. So our bronchial epithelium, we wanted to see tight junctions and mucus expression. And we are seeing that. We're seeing the tight junctions in green and mucus expression in magenta. Then with our smooth muscle cells, we want to see that they have the ability or are expressing the proteins for contractility. And we are seeing that with one of the major contractility proteins, the alpha smooth muscle actin, stained for in green there. So now we know that our cells are what they say they are. The next thing is to evaluate our tear. And again, we're seeing a similar trend that we saw previously with the Calu-3 monoculture, where the tear is consistent in the perfused system in comparison to the static, where it is a lot more variable throughout the days and between wells. In a bit more detail, we can see the spread of data in the static monoculture is very large in comparison to the co-culture. And the co-culture reduces that variability. But the combination of the co-culture and the perfusion has reduced that variability even further. And we can also see that reduction in the monoculture. We also optimized a mucus quantification assay using Alcyon blue. And we could quantify mucins by as early as day 3. And by day 7, we were seeing a significant increase in the amount of mucins expressed by our Calu-3, both in the mono and in the co-culture. But again, the combination of the co-culture with the perfusion was creating a more mucus barrier from the Calu-3 cells. So we're seeing more mucin being expressed. This is also shown in the qPCR analysis, where we're seeing, again, the co-culture Calu-3 model in the perfusion is increasing its expression of MUC5AC mucin. We also did some histological staining to see what that looks like, and we can see in the blue there those mucins that are stained by the Alcyon blue on the Calu-3 epithelium. So now, assessing that barrier function, how does the barrier change with the co-culture? So in the static, we don't see much of a difference, no significant difference. But we are still, again, seeing that same variation between wells, which isn't the best. But then, again, another thing that we're seeing with the combination of the perfusion and the co-culture is we're seeing a tighter barrier in the co-culture in this perfused condition. And the perfused as a whole, once again, is reducing the variability throughout the plate. So well to well is more reproducible. Following on from the initial mucin expression of the qPCR that we generated, we also looked at ciliated cell expression, which is also increased, and OCT1 transporters, so a cation transporter that has been indicated in the transport of drugs such as salbutamol. So our perfusion is enhancing our bronchial phenotype. The perfusion also increased the differentiation of the smooth muscle cells, and we can see here using a differentiation marker of smooth muscle, we can see the perfusion and the co-culture is combined, is creating a more differentiated, more mature cell layer. And here we see that contractility protein again, alpha smooth muscle actin, and how the co-culture is increasing the potential for contractility in these cells by increasing its expression of alpha smooth muscle actin. So to conclude, we have successfully developed a co-culture model with epithelium and smooth muscle within an MPS system. We have enhanced the bronchial epithelium and bronchial smooth muscle phenotypes with a faster rate of barrier formation and less variability. That variability decrease has enhanced our statistical power and can potentially increase the throughput of our model. With that, I would like to say thank you to the organizers for inviting me to speak, and a big thank you to my supervisory team, especially Professor Dara Manane and Dr. Emily Richardson for their continued support and help. And thank you for all of your attention, and I will be happy to take any questions.